All right, so this is 2007B, question 6. And scientists interested in preserving natural habitats and minimizing the possible extinctions of certain bird. Hold on just a moment. Certain bird species conducted a study to determine if it is better for conservation groups to purchase a few large nature preserves or many small. So we're looking to know whether or not, hey, we should purchase few or large because we want to decrease the extinction of birds. The scientists studied 13 randomly selected islands of different sizes to determine the risk of extinction for bird species. Islands are thought to be good imitation of what would happen in nature preserve because of their isolation. If a species lived on only one island, it was considered to be at risk. Scientists have determined that whether or not one species becomes extinct is independent of whether or not another species becomes extinct. In 1990, scientists counted the number of at-risk species on each of the selected islands. They returned to each of these islands in the year 2000 to see whether the species still existed on the islands. Species that were present in 1990 but absent in 2000 were considered extinct. Data collected by the scientists are given on the table below. And they give us this table with a lot of information. The first thing they do, they just number the islands 1 to 13, but then they give the area in square kilometers, the number of species at risk, the numbers of species went extinct, and the proportion of those that did go extinct. So I should be able to go 8 divided by 75 and get that value, 3 divided by 67 and get 0.04, et cetera. And you can just check that out to verify. So the very first question they ask is, one scientist involved in the study believes that the large islands, those with area, and they're defining large islands as those with greater than 25 square kilometers, are more effective than small islands, those with areas of no more than 25 square kilometers, for protecting at-risk species. So they basically say he believes that fewer birds will go extinct on the large islands as a proportion compared to small islands. The scientists noticed that for this study, a total of 19 of the 208 species on the large islands, sorry about that, it'll lighten back up in just a moment. The lights went down in the room, where a total of 66 of 299 species in the small islands became extinct. Now, I want you to look at this. We basically have two groupings here. We have two groupings. We have large islands and we have small islands. And we have data that was counted. All right, the fact that I have two groups with counted data, I'm looking at some sort of proportion. Either that or a chi-squared, but since I only have two groups, proportion makes sense. All right, you need multiple groups to be looking at the chi-squared. So assume that the probability of extinction is the same for all at-risk species on large islands and the same for all at-risk species on small islands. Do these data support the scientists' belief? Well, what was their belief? Their belief was that large islands were more effective at saving bird species than small islands. Then they say give appropriate statistical justification. When they give me that general term, they're saying you need to run some sort of test, all right? And because in this case, I have two sets of counted data, I'm gonna say this is gonna be a two proportion hypothesis test. Now, please keep in mind, they also told me that I have two groups, a large island and a small island. So I get to start off by running a two proportion hypothesis test. And it should look something like this. My null hypothesis, the proportion of the large equals the proportion of the small. And then I say the proportion of the large is less than the proportion of the small. And you're like, well, wait a second. They said it was more effective at saving. So let's look at my definitions. And you have to provide these. The true population proportion of birds going extinct on large islands, the true population proportion of birds going extinct on small islands. So what this is saying, or what my alternative is, is that the proportion of birds going extinct on large islands is smaller than the proportion of birds going extinct on the small islands. So the proportion going extinct on large islands is less than that going on the small islands. And that's consistent with what they were saying. But it's critical that you make the definition, all right? My conditions, they told me it was a random sample. So all right, random sample given. I need to check the Goldilocks, not too big. So N needs to be less than 10% of the population. Well, they had 299 species. So 200 not divided by 0.1 is 2,999. There are probably more than 2,999 species of birds. I know that. Okay. The next thing, is it big enough? Continuing with the Goldilocks. And they told us that we had 19 on the large island that went extinct. Well, 19 is bigger than 10. And then we had 208. And 208 minus 19 gives me the 189, and that's greater than 10. On the small islands, 66 went extinct. 299 minus 66 gives me the 233. I guess I should probably add that for you. And over here, it was the 208 minus the 19. All four of these were greater than or equal to 10. And remember, they all have to be greater than 10. So consequently, because they're all greater than 10, both samples are large enough to use the normal approximation. All right. So we have to make this statement. This is not an optional statement. You have to say both samples are large enough to use the approximation once you've verified those conditions that they're greater than 10. So on the large island, what proportion did go extinct on the large islands? Well, we had 19 out of 288, or 208, excuse me, 19 out of 208. So about 9%. And Q, or Q hat, which is basically 1 minus P hat. So 1 minus that gives me 0.9086, and I'm just going to need this for a formula later. On the small islands, it's 66 divided by 299, or 22% went extinct. And so 1 minus that, these are the proportion that did not go extinct. Proportion didn't go extinct, extinct, did not go extinct, and those that went extinct. So we're running a hypothesis test for a two sample proportion. And the basic formula is this: the large island minus the small island, but we have to combine. And the reason, and I want you to understand this because every now and then they ask this, is not common. But basically right here, we pooled. And this is the only time we do that. But why did we do that? Notice right here, I said the proportion of the large equals the proportion of the small. So our assumption is that they are the same. Well, if they are the same, and when I look at these two values, this one over here was 9%, and this is 22%. So they're clearly not the same. So my best estimate would be to combine them together to make them go together to make them the same. So that's what I'm going to do. So I'm going to combine these together and then make them the same. And so this is 19 over 208 for the first one, plus 66 over the 299. When I do that, I get 0.1676. You must show this work. Yes, I know the calculator will do this behind the screen, but you have to show this work. All right, continuing on. We're now going to plug into our formula. So first off, proportion extinct. This was for the large island. This is the proportion extinct for the small island. All right. And hold on for just a moment, because I apparently have some typos here that I need to address. I'm going to put this on pause. Okay, so excuse me for the error, but let's talk about this. This is going to be the large island extinction. This is the small islands extinction. This is my combined proportion of 0.1676. 1 minus that is 0.8324. And then we have the sample from the large island and the sample size from the small island. So how do we run this on the calculator? Because the calculator is going to help us get our answer. We're going to go stat test, to proportion, z test. If I go to the right spot, to proportion, z test. We had 19 species out of 208 go extinct on the large, 66 out of 299. Be very, very careful with this. Make sure that your direction here matches what we have up here, and we have a less than. And when we did this, we ended up getting a very, very small, well, our z-score of negative 3.8, and then we ended up with 5 decimal places. So essentially, this is 0, 0, 0, 0, and then a 6. But as soon as we get to having 4 zeros there, we can say that our p-value is approximately 0. So since our p-value is approximately 0, we can say that it's less than any reasonable alpha. So I chose 0.01. So consequently, I'm going to reject the null. I'm rejecting that they're equal, and I'm believing that the proportion of going extinct on a large island is less than that on a small island. So we're just going to go ahead and clean this up and write our conclusion. And our conclusion is this: our p-value is approximately 0. We reject the null. There is sufficient evidence at alpha equal 0.01 to suggest that the true population proportion going extinct on large islands is less than the true population proportion of birds going extinct on small islands. Large islands appear to be more effective in preventing extinction of birds. And we wanted to know this because we wanted to know what size sanctuaries we should want to provide, large ones or several small ones. So this is basically, hey, we're going to go ahead and run a complete hypothesis test. And typically for a normal problem, this would probably be the entire problem. But because this is a question 6, this is going to continue on. All right? This is going to continue on. So because we have to scare people, we make this as long as possible. We have another scientist who worked on this study and thinks that the proportion of species that became extinct is more directly related to the size of the islands than simply to whether the islands groups are as small, large or small. So basically they're saying, hey, there's a relationship. The scientists investigated the relationship between the proportion of extinct birds and the area in square kilometers of the island. A least squares analysis was conducted and the proportion of extinct, and this was not a typo. They did this to upset you. They included natural log to upset you that day. We haven't done a natural log regression. No big deal. We're just going to continue on and act like, hey, we know what we're doing. Again, they're just trying to shock you. Regression analysis output, the scatter plot and the residual plot are shown below. And so you notice that they have the natural log of the area written there. This right here is my y-intercept, and this would be my slope. And so if I were actually writing this, they didn't ask me to, but I'm going to go ahead and do this. This would be y hat equals 0.28996 plus, actually minus 0.05323, and instead of x, it would be the natural log of the area. all right, the natural log of the area. A little bit different, but that's what they gave us. Well, when I look at this, this is what they give us as our scatter plot. And I'm going, gosh, that's pretty linear scatter plot. That's a good sign. Pretty linear looking scatter plot. And when I look at this, the points appear to me to be very random. So consequently, I think they have an appropriate model. And it says, estimated the slope of the least squares regression line. And you're like, well, wait a second, they did that. Then it says, using a 95% confidence interval, interpret your answer in the context of the situation. So basically, I need to create a 95% confidence interval. So once again, I'm going to go through all the steps that I would go through on a recipe card. And the step basically says, you know what, I'm going to define X and Y. Let X equal the natural log in kilometers of the island. Let Y equal the proportion of birds that went extinct. Beta 1 equals 0. Beta 1 does not equal 0. This will always be the case. All right, this is what we're looking for, whether or not there's a relationship, unless they have a direction, which is rare. So the null, there is no linear relationship between X and Y. The alternative, there is a linear relationship between X and Y. I highly recommend that you do it exactly as I did. Define X and Y, then write it symbolically, then write it in words. All right? I highly recommend that you approach it from that standpoint. Then we have to define beta 1. Let beta 1 equal the expected change in proportion of extinct birds for every 1 kilometer increase in ln of area, or natural log of area of the island. Conditions. Well, they told us it's a random sample. The next thing, the scatter plot needs to be somewhat linear. Well, that looks pretty linear. Finally, there's no residual there's no pattern in the residual plot. And as we said earlier, our residual plot was random with no pattern. So that's satisfied. The one thing we cannot check on this is we really need the graph of our residuals to be normal, or to be not be able to have a pattern to them, or not skewed or anything. We don't have that information. We can't do it. So we don't have to. We're just going to leave it off and address these three. Now, how do I do this? Well, first off, my sample size, I had 13 islands. So my degrees of freedom is going to be 13 minus 2, which is 11. All right? And my formula for doing a confidence interval is my slope plus or minus t star times the standard error of my slope. My slope itself came from right here. The standard error of my slope came from right there. So there's my slope, and there's my standard error of my slope. Once again, I just pulled them off the table. Slope and standard error of the slope. But I need to calculate my t star. Well, they asked me to do a 95% confidence interval. And we already said our degrees of freedom in this case was 13 minus 2, or 11. So second vars, inverse t, parenthesis 1 minus 0.95, close parenthesis, divided by 2, degrees of freedom, 13 minus 2, or just 11, whichever you want to type in. And I end up getting 2.2009. And that's where I got that from, 2.2009. I know it's not fun, but at this point I get to solve it by hand. And basically I'm going to go negative 0.05323 minus 2.2009 times 0.00618, 618. That gives me my lower part. I do the same thing for the upper part, negative 0.05323 plus 2.2009, parenthesis 0.00618. And we get negative 0.0396. Now, one thing I should notice is it doesn't contain 0. If it's 0, there was no linear relationship. If it doesn't contain 0, there is a linear relationship. So we are 95% confident that the true population slope for the proportion of birds that went extinct for every 1 kilometer increase in natural log of area of the island lies within this interval. All right? We know that it lies within this interval. And basically what it says is that as the island increases, as the island area increases, there is a decrease in the proportion of birds that go extinct. And we know that because both are negative. So we can go ahead and make that claim. I'm going to pause and let y'all get some copying done for just a second. So in part A, the scientists assumed that the probability of a species becoming extinct is the same for each of the large islands. Similarly, the scientists assumed that the probability is the same for each of the small islands. Based on your answer in part B, do you think this is a reasonable assumption? Well, what did we show in part B? What we showed was that there is a relationship. And remember, if there's a relationship, they can't be independent. All right? So the fact that the interval does not contain 0 indicates that there's a relationship. And because a relationship appears to exist between island size and extinction, the assumption of independence is not reasonable. All right? If 0 had been in the interval, then we'd say, you know what? The assumption of independence is plausible. All right? And we like the word plausible. All right? Plausible is a really good word. All right? But because it's not in there, we can't say that it is plausible. It does not appear reasonable. It's not plausible. Continuing on. A conservation group with a long-term goal of preserving species believes that all at-risk species will disappear whenever land inhabited by those species is developed. It has an opportunity to purchase land in an area about to be developed. The group has a choice of creating one large nature preserve with an area of 45 kilometers and containing 70 at-risk species, or 5 small nature preserves, each with an area of 3 kilometers, and each containing 16 at-risk species. This is kind of important information. 45 kilometers, 70 at-risk species, or 5, each with an area of 3 containing 16. Now, please note, 5 times 16 means there's 80 at-risk species. In the small, if we do the large, we only have 70. And they have a goal of preserving the most species. So, which choice would you recommend and why? Well, we showed that there was a relationship between size when we ran the regression. And since we showed that there was a relationship between size and extinction, we probably should work with the linear relationship. So what was our equation? Y hat equals 0.28896 minus my slope, there's my y-intercept, there's my slope, times the natural log of the area. So I divided this up into large islands and small islands. And on the large island, all I did was I took the 0.28896 minus the natural log. And even now, even though I've recently done this problem, I never remember where natural log is. It's down here, minus natural log of 40, oops, I forgot the slope, minus the 0.05323 times the natural log of 45. And I end up getting 0.08633. That's the proportion that would go extinct. So if that's the proportion that go extinct, so this is extinction. This is the lives or survives. Well, how many? We had 70 species, so we'd expect 63.9 species to survive. On a small island, I did the same thing and I plugged in 3 and I go, okay, we expect 23% not to make it. 1 minus 23 means 77% are going to survive. Well, we had 80 species and we multiply it and we go, all right, we expect 61.56 species to survive. So I expect 63 bird species with a large. I expect 61 here. This has 91%. This is 77%. Large definitely saves better. And I need to not just leave it at this. I need to make a concluding statement. The concluding statement is the conservation group should choose the large island because the large island results in a greater proportion of bird species being saved, and because the total number of bird species being saved would be greater than for the smaller islands. The question was, what if the proportion saved is higher for one, but the number of species saved is lower for the other? Which one would you choose? Based on the way they phrased the question, I would have gone with the number that survived based on the way they phrased the question. However, because that one's going to save the most species, the largest proportion, and their interest, they said that was their long-term was preserving as many species as possible. That said, if you made the argument for the proportion, saving the greater proportion, you probably would have been okay on this particular problem. That's the type of thing that they tend to give you a little bit of grace on. But if your goal is to save the most species, I would have gone with the most species on this problem. And I'm not. Okay, we're recording.
Okay, so there are parts A, B, C, and D. You can think of them as kind of like each of those letters are a point. For part A, they're looking for 4 main components. The first component that they're looking for in part A is that you've identified your alternative and null hypothesis, and that you've also identified your parameters there. Then for the second part they're looking for is that you've met conditions and that you stated what kind of test that you're going to do. As long as we write the formula, that counts as naming the test. So we are already in the habit of writing our formula down. So most of us are covered, even though we didn't name the test specifically. The third part that they're looking at is your work to make sure that there aren't any major errors in there. And your work should come out with a p-value and your test statistic value or your z-score there. They'll be looking for that as part of the mechanics or your work. And then the fourth part is that you make an appropriate conclusion. So if you did 3 or 4 of those parts, you get an E for part A. If you did 1 or 2 of those, you get a partial for part A. So there is some wiggle room even in that first section. All right, so next we're going to look at part B. Part B is kind of the same thing because we're running another test, that it's going to be broken into 4 sections that they're basically looking for. The first part of the section that they're looking for is your null, your alternative, and your identifications of all the definitions. Make sure that these are all well defined. Without defining what each of these parameters are, you're already knocked down from a whole point to half a point. So you don't want to miss out on those. Also, for that first part, they're looking for your formula, B plus or minus RT times SB. Part 2 is the conditions that are met. Part 3 is your work, your DF work, and us calculating by hand your confidence interval. And then the 4th thing they're looking for is that you make the right summary statement about your confidence interval in context. So again, if you did 3 of the 4 parts, that's essentially correct for part B. If you did 1 or 2 of those, you get a partial credit. So far we have parts A and B that you could get up to an E for each part. So you might have 2 E's right now. All right, now part C. Part C is looking for 2 main components. You need to come up with a conclusion that assumption of independence is not reasonable, and you need to justify it. And our justification was that 0 is not in the interval. As they gave a lot of different wiggle room about why. Basically, they took so many things. Even if you came up with that it was reasonable because of your work that you did incorrectly, there was a chance that you could still get an E on this part as long as all your logic made sense. But if you made a statement about reasonable or not reasonable and you had absolutely no justification at all, that's always a 0. So you could get an E or a P on part C. And then for our last part, part D, again, there was some wiggle room on how you did your work, but basically they're looking for a comparison. Your comparison cannot come directly from the prompt. So they listed out specifically that you just talked about the 70 at-risk species, or 5 from the small nature preserve and the 3. If you made a conclusion just based on the givens in the prompt here, that was incorrect. So if you did some calculation work like Mr. Spencer did and did a direct comparison, or if you used parts A through C to make a comparison, that might get you partial credit. So you can get an E, a P, or an I for part D. All right, this is one of those problems that they looked at it kind of holistically. So you had parts A, B, C, D. If you got E's on all of that, that was definitely a 4. If you had 3 E's and 1 partial, they might bump you to a 4, looking at it holistically, if you were close. Like if that one of those P's came from getting a 1 or a 2, like on part A and B, like when we ran our test. If you were really close to getting a 3, like you're on the cusp between a 2 and a 3, that might bump you to a 4 score. And they did that a lot with the half points on this. So 3 E's is a 3, 2 E's and 2 P's is definitely a 3. If you had 2 E's and 1 partial, you might get a 3, just depending on that partial. If you almost had a partial on another part, you might get bumped at a 3 because they look at it holistically. 2 E's is definitely a 2. 1 E and 2 P's is definitely a 2. 4 P's is definitely a 2. And so all those other half scores or half points, they look at it holistically, the whole body of work, to see if they can bump you up to. And like Mr. Spencer said, people who are shooting for 5s on their AP exam, we're hoping that you make a 2 on question number 6. Question number 6 is weighted more. So just getting a 2 on question number 6 is a great achievement.